Okay, so in this class we will discuss about the strangeness and conservation laws. So let's start with the strangeness. Strangeness property. So this is a property which is associated with some particles. They are called as strange particles, and they have some different or particular properties. For example, if you consider their properties, important properties of such strange particle. So by means of strange particle, you can have that counts, which we said K plus this. Then we have hyperons. Sigma, Pascal. Then we have those hyperons. These are the strange particle. So what is the importance of this strange particle, or what is the strange behavior associated with this strange particles? The first one is that they have associative production. Associative production, which means that they always produced as pairs. They always produced as pairs. So that's the first property. They always produce as pairs. That is called as associative production. And second one is that the production through their production through strong interaction, and decays, the decays through weak interaction. This is the strange behaviors observed with these particles. These particles are called as strange particles. So they always produced as pairs, and when they produced, they produce their production through strong interaction, and their decay processes will be through weak interaction. For example, if you consider P plus minus, that will give you lambda 0 plus A0. Yeah, so these are the pair of strange particles, lambda and K. So they always produced as pairs. These are not strange particles. This is proton and pi 1, this is pi minus, and that when they interact each other, they produce this lambda 0 and K, that is emission. And these two are strange particles, so they always produce as pairs. And this lambda 0, if you consider this lambda 0 will be decayed into a proton pi. And this process, this is weak interaction. And this one is strong. They are always produced in strong interaction, but they decay into some other particle through weak interaction. And an exception for this particular property is for sigma 0, that decaying into lambda 0 plus gamma. And this is electromagnetic interaction. So these are not weak interaction. This is not weak interaction. So only exceptional case is this reaction of sigma. So for all other cases, we have those strange particles which will be decayed to some other particle through weak interaction. And they always produce in strong interaction. That's why these particles are called as strange particles. Now, if you want to calculate the strangeness of the particle, this is another number. So this is strangeness of particles. So how we can calculate the strangeness of particles? So then we have to consider the Gell-Mann-Nishijima formula. And that is given by Q equal to I3 plus E plus S by 2. Also B plus S is called as hypercharge. You can replace it with Y. So anyway, Q will be equal to I3 plus B plus S by 2, and you have B is nothing but the baryon number, and S is the strangeness, and then I3 is the Z component of I, Isospin. I will discuss something about this also. So this I3 is third component or Z component of the isospin associated with that particle. Q is the charge of that particle. B is the baryon number. S is strangeness. So you can have S that is equal to Q minus I3. So this is the Q, and then this. So 2 times Q minus I3 minus. So this will be the expression calculated strangeness of any particle. Okay, for example, if you consider K plus, in case of K plus, you have Q equal to 1, positive 1, and B, which is 0 because K is meson, not a baryon. So B is equal to 0 and I3 equal to 1 by 2. I will talk about this, how this is coming. And then we have K0 also. Okay, first I will calculate this. So from this we can calculate what is strangeness. Strangeness will be 2 times Q means 1 minus I3 is 1 by 2 minus B0. So this will give you 1 minus 1 by 2, that is 1 by 2. So this is nothing but 1. So here you have strangeness which is equal to K plus. Similarly, if you consider K0, K0, then you have Q equal to 0 here, V equal to 0, you have I3, which is equal to minus 1 by 2. So that will give strangeness, which is equal to Q is equal to 0, so 2 times 0 minus I3 is minus 1 by 2. This will also give you 2 times plus 1 by 2, so that is 1. The strangeness for K mesons equal to 1. And if you want to calculate, for example, sigma plus, then Q equal to 1, B equal to, what is B for this sigma? Sigma is a baryon, B equal to 1. Then you have I3, which is equal to 1. And that will give you S, which is equal to 2 times Q is 1 minus I3 is 1, and then baryon number is also. So this will give you minus 1, minus 1 becomes 0, and this minus 1 remains. So strangeness for sigma plus is. So this is how we calculate that strangeness. Now I3 is the third component or Z component of isospin, and we already told about isospin. Isospin is calculated from the expression is multiplicity. Multiplicity given by m equal to 2I plus 1. Okay, and where I is the isospin. So if you consider any system, for example, sigma, you can consider sigma. So sigma, if you consider, in this case, you can see here plus, so sigma plus I will consider here. So sigma plus, if you consider, what is that multiplicity? Multiplicity m will be equal to 2I plus 1. But m, m is in the case of sigma, that is number of particles in this group. That is the multiplicity. So that will be 3, because you have sigma plus, sigma 0, and this we are not considering antiparticle. Okay, so sigma plus, sigma 0, sigma minus. How many particles are present in that group? So that is 3. So 3 equal to 2I plus 1, and this will give you this will give you 2I plus 1, that I equal to 2 by 2. That's 1. So for sigma plus, you have the isospin, which is equal to, or in general, like I should say, in general, we have for sigma class, sigma group of particles, we have this isospin I equal to 1. Now we have 3 different components for this particular isospin, and this can be, so I is the isospin, that is 1. And if you want to calculate what is I3, that is the third component of isospin, that can be I3 or IZ, you can represent Z component of isospin, and that can be plus 1, 0, and minus 1. Okay, and the highest charge particle in that group, particle with the highest charge, that will be associated with this positive, highest positive isospin. So that this one will be sigma plus 0. The isospin corresponds, Z component of isospin corresponds to the plus is plus 1. Z component of isospin corresponds to the this is how we calculate the isospin and third component of isospin. And from that, you can calculate the strangeness by using this Gell-Mann. Okay. Now we will discuss about the energy conservation of the particles or the interactions. So this we already know in many systems. There are different types of conservation. We already discussed about the baryon number conservation, electron number conservation, all those things. Okay. Now we will discuss about the energy and momentum conservation. Also, we have that strangeness conservation. Strangeness before reaction and after reaction should be same, otherwise should be curved. Otherwise, you have the phase value which is equal to 0 plus or minus 1. Then according to that, we will say that the reaction is strong or weak. Like that. Okay, we will come to that. But the energy and momentum conservation first, that we'll discuss that. Then we'll go to the other part. So in case of energy conservation, or you can also say that this is associated with that momentum conservation. So let's consider this separately. So energy conservation. Energy conservation, for example, if you have a pi minus, which is decaying, okay, pi minus which is interacting with the proton, we already discussed about this. So that will give you sigma minus plus some K plus. So sigma minus plus K plus, these are strange particles, they always produce. Yes. So in this particular, I think we discussed about this. We just here no, this is this different set. Calm down. Anyway, so this is this. Let's consider this reaction. So here 140, we have different energies associated with these particles. Okay. So, for example, in this case, we have 140 here, then 38.3, and here 1.7, here 400. So, if you consider this reaction, we have in this part we have total of 128.33, and here we have total of 100, 1690 almost. Okay. So that reaction, if you consider, then their energies will not be conserved. So this reaction will not be possible until we provide some kinetic energy to those particles. So this reaction will not happen until we provide kinetic energy. This kinetic energy for those say that interacting particles. Okay. Then only this energy will be conserved. So here we are considering those masses corresponding to each particles. For example, if you consider that in terms of energy, then that will come as A plus B, that is going to be plus 2. Then this MAC square plus MEC square, that should be equal to MCC square plus M. Okay, so this should be there, that energy should be conserved in each action, then only that reaction happen. If the energy is not conserved, then such reactions will not happen. Another example, for example, decay process. Consider any decay process. Let's say some P is going to become Q plus R plus S. This is the decay process. Then similarly to this, MPC square will be equal to MQC square plus MRC square plus MS. Yeah. Plus some kinetic energy also will be there, because they will be coming out of this interaction used, which will be used as the kinetic. Okay. So if K equal to 0, this kinetic energy is equal to 0, then MPC square should be equal to MQC square MRC square plus MSC square. And if kinetic energy is non-zero, then MPC square must be greater than MQC square. I hope you understand. If kinetic energy equal to 0, then MPC square will be equal to MQC square plus MRC square plus MS square. Kinetic energy will become 0. If kinetic energy is non-zero, which means that kinetic energy is there, then MPC square must be greater than square plus MRC square plus MS, because some energy from this MPC square will be for that kinetic energy. So this MPC square should be larger than this total energy of those particles. If you consider another decay process, proton, which is going to become proton plus and positron plus, no? This is having 938. Here we have 939, almost masses, and here we have 0.511. Okay, so this mass energy, if you can see mass or energy, if you consider in this particular reaction, here we have 939 plus some 0.511, and we have more G and kinetic energy. Okay, so this side is heavier, so this reaction is not. So that is about energy conservation. Energy should be conserved in any area. Similarly, if you go for the momentum conservation, so in the case of momentum conservation, this also we know, because this is also conserved in all systems of reactions. Then we can say P in momentum of the incident particle or interacting particles, that should be equal to the total momentum of the final. For example, pi plus, which is decaying into mu plus some mu neutrino. So the suppose this pi plus, which is at rest, this is at rest before decaying. So this pi will be equal to, so initial momentum, pi means initial momentum, that will be equal to 0. Then that implies p mu plus p mu mu, sum of these two, that should be equal to 0. It should be 0, then only this particular reaction will happen. In other words, I can say that p mu will be equal to minus p mu. P mu, which means that the pi plus, this was here initially, that decayed into mu muon and no. So this will be decayed into mu and mu meter. They should go in different direction, in opposite direction after process. So this should go in the opposite direction. Then only that p mu. Then total momentum will be equal to 0 when pi plus is at rest. Okay? If the pi plus was initially at rest. Another example, if you consider an electron which is combining with a positron, you are familiar with this. This is nothing but that pair annihilation process. So in this case, suppose you are getting only one gamma, one photon, and in this case, this will not be conserving that momentum because when you consider that from the center of mass frame, okay, we can have those electron. For example, this electron is coming in this direction. This positron which is coming in this direction. And if you have that gamma radiation which is going in this direction, but in this case electron is in this direction, positron in this direction. So if the resultant particle is in this direction, then the momentum will not be conserved because one is in this direction and other is in the opposite direction. So they will be having, they have to be cancelled, their directions cancelled here. So that will not be the case here if you consider that in center of mass frame and if electrons and this, and there should be some photons which are going in this direction also. So in this reaction, this is not going to happen. But if you have two photons in this reaction, so a photon with a higher frequency that will not be going to come in this particular reaction. Instead of that, we have first photon gamma 1 plus gamma 2. So this is your gamma 1 and this is your gamma 2. This can be possible. So that's why we have always in that pair annihilation process, we will be having two photons. We can also have one photon with high energy, but that never observed. We always observed two photons with low energy. For example, this photon can have five. I'm just putting some. Let's say this will be having 0.511, so 1. Instead of this much of energy, this will be shared with some 0.511 here, 0.511 here. Okay. So this much of energy can be shared with these two photons. So always these kind of reactions we can observe, but this reaction we will not observe because the momentum. We always observe this. So in all those particle interaction, momentum also we conserve. Now, if you look for the angular momentum conservation, for this angular momentum, this is a linear momentum we have here. And now we have angular momentum conservation. So for the case of particle interaction. So in this case also, if you consider the different angular momentum, for example, if you have sigma 0, which is decaying into pi 0 plus photon, gamma. Then this sigma 0 is having spin half, pi 0 is having spin 0, and gamma is having spin, because this is boson, this is fermion. So this will be having spin, integral spin, that is 1. Here also we have spin which is 0, and this is having half integral spin, that is 2, because this is fermion. Okay, so then when you consider this case, you have initial, in this particular case, we have to consider the total angular momentum, and that is given by J value. So that will be from J1 plus to J1 minus J2. Now, if you consider here, we have J I, that is incident particle J value, that is 1 by 2. Here we have J final, that is equal to, here we have 1 and 0. So J final will be 1 plus 0 to 1 minus 0. Okay, so that will be, we'll just write here. So this will be from 1 plus 0 to 1 minus 0. That will give 1 and 0. Sorry, this will be 1. Okay, so this particular reaction, which is forbidden, because we have final angular momentum which is 1, we have initial angular momentum which is half. So this reaction is forbidden. This is forbidden. So this particular reaction is not allowed. So this is forbidden reaction. Similarly, if you consider any familiar reaction, for example, neutron, which is going to become a proton plus electron plus antineutron. So this is simply that negative beta decay process. We have spin half polar fermions here. So this will be half, this will be half, this also half, this also half. So the J in value, that is half, and J final, initial value is half, J final will be equal to, initially you have to take this 2, so 1 by 2 plus 1 by 2 will be 1, 1 by 2 minus 1 by 2 0. So you have to deal with that. This 2 will give you 0 and 1, that has to be added with this. So 0 plus 1 by 2 is 1 by 2, 0 minus 1 by 2 is also 1 by 2. That take only the equal part. Okay. Then you have 1 plus 1 by 2, that is 3 by 2, and 1 minus 1 by 2 is already 1. So 3 by 2 and 1 by 2 are the possible combinations for final J. Okay, so in this particular case, we have 1 by 2 here, and we also have 1 by 2 in the initial state or initial for the particle. So that this reaction can be possible through this two angular. So angular moment is conserved in this way. So this reaction is possible. The reaction is allowed. Okay, and if you consider those spin, I will just give a hint for that. All leptons we have to take. Leptons. All leptons are having spin half. Similarly, quarks and antiquarks, or quarks and antiquarks also having spin half. And if you consider any mediators, all mediators, which means that force carriers, they are also they are having spin is equal to 1. And for the case of Higgs boson, that is having spin is equal to 0. And similarly, if you consider for fermion case, or all the particles, if they are fermions, this, fermions, they will be having half integrated by 2, by 2, by 2, etc. For bosons, particles which are bosons, they will be having 0, 1, 2, 3, etc. Photons are having this 0 spin. And if you consider that leptons, we already discussed it for leptons, we have spin off. And if you consider mesons, uh, we can have spin one particle, with the mass. They can have spin is plus 1, 0, this one. And if there is not any mass, spin one particle with no mass. There is no mass. Then in this particular case, they will be having spin plus 1. We will anyway we'll discuss about this spin, at least for all those particles later. We'll draw those diagrams and all these things. So let's move to the next section. So the angular momentum also should be conserved in all particle interactions. So we discussed about energy conservation, linear momentum conservation, as well as angular momentum conservation. Now we will discuss about some important properties. The first one is the charge conjugation. Charge conjugation. So charge conjugation, we represent this as C. So this should be conserved, or this should be symmetric. So that means that if you are having any reaction, change that charge from Q to minus Q or particle to antiparticle. Which means that make that charge charges particle from Q to minus Q. This means that from particle to antiparticles. For example, if you are having pi plus, which is decaying into mu plus plus. If you take the charge conjugation of this, then you will be having pi plus becomes pi minus, and mu plus will become mu minus plus. If both of these reactions have same probability, then the reaction conserves the charge quantity. Okay. If both of these reactions or interactions, decay has, if both of these reactions has same probability as, then these reactions conserves charge conjugation. Another important symmetry is that the time reversal symmetry. So before we go to that time reversal, we first discuss about the parity symmetry, parity conservation. So that we already discussed about this parity. We discussed this beta decay process. So parity is nothing but the flipping of those axes. Okay, so that is nothing but a mirror image of the real world, you can say. Okay. So if you are having your x, y, and z directions, x, y, z, and x axes, take the parity operation, that is nothing but this parity operation, that will give you your y in this direction, z in this direction, your x will be in this direction. So this is your parity operation. Now what will happen to the left-handed particle becomes, in this particular operation, left-handed particles behaves right-handed particle if you have that parity conservation. So after parity operation, left-handed particle behaves as right-handed particle. So if you use the charge conjugation and parity for left-handed to right-handed, method. Inversion, we have CP symmetry. So actually in parity symmetry, if we consider parity conservation, this is not conserved in all the reaction because we already discussed in beta decay violates parity conservation. So I will just talk about it. So we have that experiment, this is the Wu experiment, where we have cobalt, which is decaying into nickel. We already discussed this in beta decay process. So I'll just cover this in here. Add that mirror here. This is your parity operation. And if we consider that cobalt, yes, which is having spin direction, which is like this. So in the mirror image also, that spin direction, if you consider, will be like this. So this will be like in mirror image, and then we have about yes, the world. This is your real world. This is your mirror world. So in this particular case, this cobalt will be decaying into that nickel, and this nickel will produce in this decay process. It is going to produce electron as well as antineutron. Okay, so the electron can be emitted in this reaction, and antineutron also will be produced in this particular reaction. Electron. So when we consider this particular case, okay, these electrons which are coming out, which are having 50% probability to go left or right. Okay, it can go like this, or it can also go into this direction, and the antiparticle can come in this direction. This is also possible because it is 50-50 chance. Both are possible. It can go left and or it can go right. 50%. Okay, but the electrons, for example, if this electron is going in this direction, which means that it is moving in the positive z direction. For example, if I take this as z and this is my y, so it is going the positive z direction in this real world, and in my mirror world it is going in the negative, sorry, positive, same positive z direction. So this is in the positive z direction in the real world. This is in the positive z direction in the mirror world. So in mirror world also it is going to the positive z direction. So electrons will be, if you consider this case, the electron will be moving. So in the mirror world it will be like this cobalt will become nickel, so nickel, and this will be, this electron will become here like this. So in mirror world also it is coming in the positive z direction. So in real world it is coming in the positive z direction. In mirror world also it is coming in the positive z direction. But consider that spin. If you consider that spin, you can see in normal experiment, if the electrons are released opposite to the spin, in mirror experiment, electrons are released in the same direction of the nucleus. You can see from here, if I take this clockwise direction, which is going to give me that spin direction like this, and anti-clockwise direction will give me that spin direction like this. Okay. So if you consider this case, which is in the anti-clockwise direction, so the spin will be opposite. The spin will be opposite to that of the direction of the electrons. Okay. But in this case, this spin, if you consider here, so this spin will be having a direction which is in the clockwise direction. You can see from here. I should in this particular case, both will be both should be having in the same direction. So this okay, here we have electron. Okay, this is okay. This will be this direction. So how it will come? So this is in the opposite direction of this electrons, which is moving in the positive z direction. So this one should be in this direction, right? So this will be having same spin. Spin will be in the same direction in both cases. So here we have the spin which is moving this direction. So the spin in both cases will be the same in the same direction, which is, for example, in this particular case, we have the electrons which are moving in the positive z direction. So this is the momentum direction. And if you consider that spin will be moving in this, spin will be in the opposite of that positive z direction. And but in the mirror world, you can have that electron which is in the positive direction, the positive z direction. But the electron spin, which is also in the same direction, which means that you can distinguish between the mirror world and the real world. So parity symmetry is not conserved in this weak interaction. Okay, so parity is not conserved in this weak interaction. Parity violates. From this we can see that. If it is conserved, then it should follow same kind of behavior in both mirror and real world, so that we cannot distinguish between the which one is real and which one is mirror world. Okay, so but here we can distinguish between this mirror and real world, so that parity is not conserved in this particular case. In this wicked. Now another symmetry, but before that we have CP symmetry. CP symmetry. CP symmetry means that you apply both conjugation of that charge conjugation and parity, and it was successful to somewhat because when you have both this action, for example, if you have these spins and angular momentum direction, if you consider all those such things for the parity conservation, and after that you change that particle with antiparticle, then that's symmetry, that CP symmetry will be, or CP charge conjugation and parity will be conserved. Okay, So in all reactions, CP will be conserved. But in 1964, it is shown that it is at even if you apply CP, that is charge conjugation along with the parity operation, still we will not be having that symmetry or we will be having it. Because kaons, they are the lightest strange particles. They will um, they will not obey this CP symmetry in some cases. Okay. So in here, what will CP symmetry means? In CP symmetry, what we'll do? We have to replace particle with antiparticles. That is charge conjugation, and the mirror flipped case. Sorry, mirror. The axis flipped. Both applied here for charge conjugation as well as the parity. And in this particular case, it was successful, and the CP symmetry was there for all those reactions. Suppose if you have any reaction, for example, A change to A become B plus C, and if you make the antiparticle of A, particle of B plus C, and this will be conserved. This will be okay. This symmetry will be there if you apply this parity also, and in that particular case you have to consider the momentum of those particles, spin of those particles, and consider the direction, and the mirror world and the real world both that should match for doing this. Okay, so after this, so this is charge conjugation, then plus parity operation on this parity operation, then you will get that symmetry or the CP charge conjugation and parity considered. That will be conserved in almost all the reactions. But in 1964, it is found that for the case of kaons, the CP symmetry violates. For example, if you are having uh, kaons, so there I will just say that these kaons can decay, for example, K0, which can decay into 2 pions, or it can decay into 3 pions, both are there. So let's say this will be having the CP eigen value, which is -1 to the power square, and this is having CP eigen value, which is -1 to the cube. Okay, which I'm not going to talk about it much details. Actually, we have charge conjugation plus parity. We have different states. First, we have to consider. For example, if you have a state K1 is equal to 1 by root 2 with K0 or K0 plus K0, which has to be abstracted from. Let's say we have some state like this, and the CP action if you put here with this K1 state, then that should give me 1 by root 2 by root 2. Charge conjugation along with parity will give me K0, will become K0 bar. Parity will make negative direction, and K0 will become K0 bar because of the charge conjugation. And then this minus is there, K0 bar. If you change that direction, that will become minus K0 bar. So that is plus, and charge conjugation will give me K0. K0 bar will become K0. This will be okay. So this is nothing but your initial K1. And then if you have another state K2, which is equal to 1 by root 2 times same kind of particle K0. Instead of minus, I am having plus here. Okay, another state. So this is K0 bar. And if you apply the charge conjugation and parity operation in this state, then you will get 1 by root 2 times this one k0 will become k0 bar that, minus, and here also we will get minus because of parity operation. Then k0 bar will become k0 because of charge conjugation, and that will give me minus of k2. So I can have this k2 will be given me will give me minus 1 as my eigenvalue. This here I will get plus 1 as my eigenvalue. As you know, any operation acting on psi will give me some eigenvalue, same state. So that eigenvalue, which is plus 1 here, this is minus 1 for these two states. So when you consider that reaction, this k0 can decay into pions, 2 pions or 3 pions. When you have 2 pions, then the associated eigenvalues will be like minus 1 square, and this associated with these 3 pions, we have minus 1 to the power cube of eigenvalue for CP operation. Okay. So when you consider this particular reaction with k0, which is decaying into pi 2 pions and 3 pions, and these two, if you consider this two case, these pions will be having more kinetic energy as compared to these pions. Okay. So that this particular case, this this particular case, otherwise I should say this is k0 becoming pi 2 pions. This is short lived as compared to this case. k0 will become pi 3 pions. These are long lived. Means that this will be having more lifetime as compared to this. So I will make this as k long and this is k short. So this k short and k long should also have the same eigenvalue of that k2 and k that we discussed here. Okay. But when we did the experiment, so the KL should always, so this KS and KL should give me, so this one is, K1, sorry, this one is having more kinetic energy, so this is KL. Okay. So this will give me, KL will give me 2 pions, and the CP, sorry, this one is KS. This one is long lived because we have more kinetic energy in this case. So this is short lived. That means that k0 into pi 2 pions. This is very rarely occurring process. This is the most frequently occurring process as compared to this one. So these are long lived. This is having longer life period. So in this particular case, KL, if when we did the experiment, it is observed that sometimes this KL decay into 2 pions. Mostly it will give 3 pions, but sometimes it is also giving 2 pions, which means that sometimes this CP eigenvalue are not same as that of this particular case. Okay. So for KL, this should be associated with the eigenvalues corresponding to that K2 state. But since KL sometimes decay into 2 pions, when we did this experiment, it is observed that sometimes we get 2 pions instead of 3 pions. So which means that this KL decays into 2 pions, which means that we are getting eigenvalue of this state. Okay, so the eigenvalues are not same as initial. So the K2 which is the one which is decaying. So the initially this K2 state is having some eigenvalue correspond to that CP symmetry. That is not the same as that of the final one, and the final one is 2 pions, which is having eigenvalue which is associated with this K1 state, which is this. So the eigenvalues of the CP operation, charge conjugation and parity, is violated in this particular case when this long-lived K, which is decaying into 2 pions. Okay, normally it should give 3 pions, and then if it is giving me 3 pions, then this eigenvalue correspond to that CP operation, charge conjugation parity symmetry, that is conserved. But when you have KL, long-lived K1s, that is going to become pions. Okay, this is not conserved, or this is not giving me the same eigenvalue of that KL, because here I am having -1 to the power square, here I am having -1 to the cube. So this is not the same. Initial eigenvalue of the CP symmetry, CP operation is not same. So this is not, this is violating that CP symmetry. So K-ons, basically K-ons sometimes show violation for CP symmetry. Then we will come to another symmetry operation, which is called as time reversal symmetry. Time reversal symmetry. And in this particular operation, we have to make the time t into minus t for this particular case. In this case, t changed to minus t. And we have to observe what will happen to those interactions, whether it is possible to have those kind of reactions. We change that time to t to minus t. Okay. So in the case of this particular symmetry, we have to change that time. So for example, I should say that E minus plus E plus becoming 2 photons. We discussed about this reaction. And if you change this time frame, that is, if you make that time reversal, then gamma 2 gamma should give me 1 electron. Okay? So this should happen when you change that time t into minus t. So the reaction should happen in the reverse way. 2 photons should give me electron. And these are time reversal or time symmetry, time reversal symmetry. That is, in the case of strong reaction, this is observed. This is okay. Time reversal symmetry is there. In the case of electromagnetic interaction, also the time reversal symmetry is obeyed. But in the case of weak interaction, this time symmetry is not. Okay. Weak interaction, time symmetry is not obeyed. But in the case of strong interaction and electromagnetic interaction, it is obeying time symmetry. Similarly, that charge conjugation, if you consider, it is electromagnetic interaction, gravity, strong interaction, all obeys that charge conjugation. Okay, if you consider that charge conjugation, C symmetry. So C symmetry, which is obeyed by the gravity, gravitational force, gravity, or it is also that electromagnetic interaction also obeys this charge conjugation, but also strong interaction also obeys this charge conjugation symmetry, which means that if you are having any of these interactions, charge conjugation is possible, which means that if you change that particles with antiparticle and check that reactions will also be possible, as same as that of the particle. So, but in the case of the weak interaction, this is not allowed the charge conjugation property. So if it is weak interaction, it violates the charge conjugation. So in that particular case, you cannot change electron to E plus or any positive charge to negative charge or neutrino, for example, neutrino. This is not possible because in weak interactions, charge conjugation is not possible. Charge conjugation symmetry violates in weak interaction. but in strong and electromagnetic gravity, all those things, it is okay. Okay. So that's all about that. Also in parity, also we already told that we can like conserved. Parity is not conserved. We already discussed about that e-educat process, and which is not having that parity symmetry or which is not conserving that. Okay, so then we introduce CPT theorem. We will discuss about this in the next class. We have both after violation of the CP symmetry, CP conservation. Then we introduced this time reversal, and when you have all these actions together, charge conjugation, parity, as well as time reversal, then the interactions are conserved, or interactions are possible. CPT theorem yet not violated in any of the particle interactions. So we will discuss about that